Thank you. Good morning, everyone. I am Nour Al Imane Toufiq, a first-year applied science undergraduate student at Mohammed VI Polytechnic University in Morocco. And today I am presenting my research abstract submitted to Habitat Marte space event titled Integrating Space Habitat Design with Next Generation Propulsion Systems, affiliated by the co-authors of MMAARS. For the agenda overview, we're going to go through the background of the study and the problem statement, the framework, then the methodology used of the data collected, qualitative data and quantitative data, then the proposed timeline, and then the analysis and a final thank you note. So for the abstract submitted, the context of the problem is studies have shown how powerful project-based learning is for STEM education, engineers and scientists trainings in particular. My vision is to strike a design of project-based learning through studying the interlink of habitats and propulsion systems of future missions, such Melissa and Gateway Space Station, to create a skill-enhancing environment for space communities by practicing simulations and building their projects, the engineers' projects. So to test out this design, this design, MMAARS will incorporate the findings and final simulations and projects in their future analog missions, as well as contributing to refining design proposals as professionals. For the problem statement, space missions are transitioning from orbital missions to a permanent presence beyond Earth. So my work is to study these future missions and build a design program for students, undergraduate and graduate students, to build the engineering communities to work together through already building simulations and projects for the future's space inclusion, especially in underrepresented groups like Morocco and beyond. The work has three scopes of studies: a technological scope, an educational scope, and operational real-world validation. For the technological scope, it's to study the two systems of space missions and rockets, which is the propulsion systems and habitat systems. Though the professionals, of course, know that they are interconnected and we cannot have one without the other. And in fact, the choice of the propulsion systems is directly dependent on the kind of space missions we're sending, especially for the payload. So my study is to study this, but it's not very apparent to the public and to not really very included people in the industry. So my work is to study this scope of the propulsion systems and habitat systems, and then by exploring how space habitats from life supports, energy systems to structural designs connect and interact with advanced propulsion technologies like chemical, electrical, and nuclear engines, especially for the Gateway Space Station that is going to use solar electrical propulsion. And by then, we're going to transact to the educational scope, which is to build the project-based learning communities for engineering communities in Morocco, basically, but in future, build global communities that is going to test this study of these propulsion in the habitat systems to build their simulations and projects. So to develop an educational framework brings together space engineering, life sciences, and propulsion by using hands-on projects and real-world analog missions to teach these concepts. And then to the operational and real-world validation is to examine how ideas about space integration actually work in real-world scenarios by using analog habitats and simulation tools to test these ideas. Now for the framework. We're actually going to, as the steps of the study is to build the first scope of the research part of studying studying the propulsion systems and the educational systems. So we're going to do a hypothetical study on life support systems like Melissa and the Gateway Space Station to study the habitat system in the Gateway Space Station. And then through this study, we're going to incorporate it in MMAARS analog astronaut missions and the university engineering communities. And then to sit on their simulations of propulsion systems to build sustainable space environments for everyone, including underrepresented groups. For the methodology, we're going to use a simulation-based and analog integrated research approach. We're going to focus on using simulations to study how propulsion systems interact with habitat needs. Through the first scope of the study, which is the research scope and the educational scope, we're going to use simulations to study how propulsion systems interact with habitat needs by using computational packages like MATLAB and JMAP models and NASA's propulsion data. We're going for our goal is to determine which propulsion options, chemical, electrical, or nuclear, best supports long-term missions to the Moon and Mars for the Artemis program. For the qualitative methods, we're focusing on understanding the educational and hands-on learning outcomes to interview observations and reflect journals from MMAARS and the student activities in their engineering communities. For the themes, we're going to use systems thinking, teamwork, problem solving, and cross-disciplinary learning. Our goal is to assess how experiential training improves comprehension of how space systems fit and work together. We're trying to integrate propulsion habitat simulations with analog training in MMAARS to clear technical outcomes and meaningful education growth, showing that true space sustainability starts with system-level thinking that we have here on Earth. So this is the steps we're going to go through in this project. Sorry, I cannot see. So we're starting first by simulations, then building our educational models to test them in the MMAARS analog missions, then get the data feedback from the analog missions and from the engineering communities and build a framework refinement. For our, So for our qualitative data, we're going to collect data by, as I said, the students and analog crew members to develop system thinking and adaptive learning through integrated propulsion habitat simulations to understand the educational transformation driven by experimental analog missions. Our source of insights, of course, are MMAARS analog missions, the interviews and focus groups of our engineering communities and the clubs we're going to build, and as well, we call them the astrolabs, and to reflect it through the journals and reports they're going to give back. Our contributors are to generate qualitative insights into how integrated propulsion habitat missions shape learning, identify potential patterns in system thinking and collaborative problem solving, inform future educational frameworks for analog missions training, and our analysis approach is to extract core patterns in learning outcomes, system interdependence, problem solving under simulated mission stress, our educational growth metrics are to evaluate understanding of propulsion habitat interdependence in cross-disciplinary design. Before I go to the quantitative data, of course, this approach of building this engineering communities is going to start in Morocco first, but we are building this network of many engineering communities across top world universities to test together this project-based learning design. For our quantitative data, Our focus is to evaluate propulsion system performance using computational simulations to compare chemical, electrical, and nuclear propulsion across payload capacities through the kilogram delivered to the specific impulse and energy efficiency, the emission duration and resupply frequency, and propellant mass and cost efficiency. Of course, all are play the role of choosing the type of the propulsion system for the space mission. The tools and data sources, we're going to use again the computational packages through MATLAB, GMAT, and NASA trajectory datasets. The MMAARS analog mission telemetry for energy, oxygen, water, and power consumption models. They're going to start from the 2026. Our expected outcomes is a statistical comparison of propulsion, habitat configuration for long duration missions, and identification of optimal integration models for Gateway, Artemis, and Mars-based scenarios, insights on balancing fuel economy, habitat, energy demand, resupply intervals, and mission duration constraints. All that the goal is to train the undergraduate and graduate STEM professionals and students to building their profiles and to become professionals. For the analysis, we have technical innovation. Technology, of course, becomes meaningful only when designed for people and purpose. Our system feedback loop is habitat demands and propulsion capabilities interact dynamically, forming a feedback-driven design cycle that improves system coherence. Student learning and innovation students is, we are trying to learn how to optimize systems trade-offs, balancing thrust, energy constraints, and long-term sustainability to generate data-informed decision frameworks for future missions architecture, and of course to make students not only specialize in one major in STEM, but to become multidisciplinary professionals. The third point is interdisciplinary collaboration, which I just mentioned, the model naturally promotes cross-field collaborations across mechanical, aerospace, and biological engineering, mirroring real missions planning environments, and for students to expand their horizons and in their understanding of STEM education. Our educational transformation is from learning about systems to thinking in systems. Our first scope is to deepen conceptual understanding. Project-based simulations help students move beyond memorization, giving them a clearer grasp of how propulsion and habitat systems interact. Our second scope is experimental problem solving through analog missions. MMAARS analog missions turn theory into hands-on systems engineering practice, strengthening real-world decision-making. MMAARS analog astronautics missions are very expanding, and they include so many majors and so many experimental hypotheses that incorporates many engineering fields, and that makes it perfectly suitable for this study. Development of adaptive leadership and competence. We're trying to reflect on learning builds adaptability, leadership, situational awareness, and mission-ready teamwork. Documented gains in engagement and innovation. The framework boosts students' engagement, encouraging innovation and creative problem solving, especially among Moroccan participants, of course, that is pushing itself to an inclusive path towards in the space industry. Our final scope in the analysis is global inclusion and capacity building. We're expanding access through inclusive education. The framework positions space education as an attainable path for students in developing regions, showing that border access begins with inclusive, locally grounded models, and that communities can build that change within themselves, and not until a space agency has to start doing so. Moroccan institutions as a scalable model. Morocco is a very strategic location for the space industry, yet it doesn't it didn't include itself in the space industry before, but now we're seeing that it's becoming very apparent and a pulsing example in it. So we're trying to enhance that scope and then prolong it to other communities. So its implementation in Moroccan universities serves as a proof of concept for other emerging regions to help build the capacity in space systems, sustainability, and technology ethics. And to strengthen global-local integration, the program enhances collaboration between global engineering, space communities, including STEM groups and MMAARS missions, creating strong links in expertise and opportunity. And to build a diverse future space workforce by providing practical systems experience and interdisciplinary learning, the framework supports the development of a more diverse, globally prepared space workforce in Morocco as to lead Africa in the space race. For our timeline, we are starting first with the framework refinement to integrate updated propulsion datasets like the solar electrical propulsion in nuclear thermal propulsion, and to improve habitat propulsion models in MMAARS mission, and to work on the simulations of adding energy and resupply optimization layers. Then our second milestone is the educational development, where we are in the process of launching student simulation labs. First, I'm working here in my university, the Mohammed VI Polytechnical University, and then building the scope on the other engineering communities and schools in Morocco, and then working our way into a network of global engineering communities to train instructors in this program and build open source curriculum for everyone to access. Then our third milestone is the analog mission expansion. The nearest one is next year, so we're going to start with that one. So to conduct it on the MMAARS missions, then test the resources limits during the missions, can then compare the field data and what we expected in our simulation data. Our final milestone is the global collaboration and publication. MMAARS is part of the IAC, so we're hoping to present our findings during it and other conferences to publish our results and expand our inclusive programs globally. Finally, in the conclusion, we're trying to integrate, to prove that integration is the key to sustainability, to integrate every underrepresented groups, because when we're trying to talk about sustainability of those groups, we can't just build this entire framework on first world countries, but we actually have to include the countries that the sustainability is focused on. So long duration missions demand synergy between habitats, propulsion, and logistics, not isolated designs. And the framework shows how connected systems thinking drives missions efficiency and sustainable collaborations. And education is the engine of progress. We're showing that project-based learning and simulations and MMAARS missions turn students into active mission designers, not passive learners. And education becomes the human propulsion systems, powering innovation in space exploration. And inclusion expands humanity's reach. So integrating Moroccan and global space education creates new pathways of access, empowering emerging regions to shape the future of space systems. Capacity building ensures a diverse, globally prepared, multi-planetary workforce. Of course, sustainable exploration isn't just about surviving in space, it's about learning, collaborating, and evolving together as species. Thank you all for listening to this presentation, and a special thank you to MMAARS and Dr. Susan Jewell for their guidance and contributions to making this work.